Greg, are you ready?
Yep, ready. You're going to start us off, right, Paul?
Yes.
Okay.
Okay, let's start. Okay, good morning, good afternoon, and good evening. Welcome you again to this World River and Delta System Source to Sink webinar series. We started this talk series in August 2020. So since then, we have already more than 90 talks. Today exactly is 94 talks so far. So as you know, we continued from 2020 to 2021. And can you believe this is almost the end? Not almost, it is the end of year 2020. So in the past 1.5 years, we have speakers from Brazil, Colombia, US, Canada, UK, France, Germany, Netherlands, Poland, Italy, Egypt, Israel, Thailand. I forgot Singapore, and China, Japan, Australia. So we have 22 female speakers. We definitely need more speakers from India, from Russia. So if you have some colleagues from there can talk about their rivers over there, please recommend them to us. So all previous talk have already archived on the Source to Sink YouTube channel. As you can see, you can access, they are free to the public. So you are welcome to use them freely for your research and for your teaching in your class. But just remember, give the credit to the individual speaker. So, okay. And also we maintain a Source to Sink a Twitter account. If you have a Twitter account, you're welcome to follow us. We will announce any new speaker every week. So it's called Source to Sink. And at the same time, next year, because the pandemic still hang around here, we really don't know when we can travel freely or we can meet face to face. We really hope we can, but who knows? But those, we still line up some talks in the spring 2022. If you are able to, if you willing to also contribute a talk to this webinar series, please let either me, Kevin Xu, Sam Bentley, or know, so we can schedule your talk. And okay, today, this is a co-host webinar series. Today, the host will be Greg Tucker from DMS, the director. So Greg, go ahead.
Okay, well, thanks, Paul. So it's my tremendous and great pleasure to welcome Professor Jaia Syvitski as today's seminar speaker. You can go to the next slide, Paul. So Jaia is an award-winning oceanographer and geoscientist whose research and community service has had literally a global impact on the field and the study of Earth's source to sink systems, on the impacts of this crazy time period that we're in now in geological history called the Anthropocene. So Jaia is a professor emeritus at the University of Colorado at Boulder. Jaia was the director of the Research Institute INSTAR from 1995 to 2007. And then after stepping down as INSTAR director, Jaia was the founder and first director of CSDMS, which is the Community Surface Dynamics Modeling System. And if you're curious about what on earth that is, I'll paste a little link here in the chat. So one quick logistical note, I actually have to leave a little bit early myself, so Kevin is going to moderate the questions and answers at the end of the talk. I assume Kevin will tell you about how to do that, whether to unmute or to put questions in the chat. But at any rate, I want to go ahead now and turn the floor over to Jaia to talk about Earth's sediment cycle in the Anthropocene.
Okay, thank you, Greg. Share. There we go. Everything looking good?
Yes.
Okay. So, hi, everyone. Hope you're doing well. So today I'm going to talk about two things, the Anthropocene that you've heard me speak about once before, but this time I'm focusing on the Earth sediment cycle. And I also think, so this is the most important part of the talk, take this part seriously. I think this is the community, the source to sink community, that should work together, develop an international project, and sort of take some of the concepts that myself and my co-authors have put together for a Nature Reviews Earth and Environment paper that's now accepted by the journal, and develop a sediment grand challenge. And I think this would be wonderful. There's a need for it at the international level. It could be done on the national level, but I really think that it would not be the same. It's an international effort that is required. And so I'm going to talk to you about that. I'd like to thank my co-authors from all over the world who've worked with me in putting together basically a review. And although the review has led to startling insights, I think that it still should be considered a review. And most of the numbers that I'm giving you, I think can be improved. And that's what this sediment grand challenge that we suggest is all about. So I'm going to explain these diagrams in detail through the talk. And so you'll see them more than once, and the numbers behind them. Okay, so how do I go forward? So,
Click.
There we go. Click, yes. You would think that would work. Okay, so importantly, when you're doing a global study, you have to have an accounting practice. And that accounting practice has to have accounting rules. So the first thing that the people who have done this before us and have decided upon is that the coastline is the best place to monitor how much sediment is involved in the global sediment cycle, how much sediment is being moved from the landscape to the ocean. And that's because so little of the sediment is moved back onto the landscape except for tectonics, which is sort of how the sediment cycle feeds into understanding how the planet works. Now, maybe you know or you don't know, but the coastline is the minimum value, or it's close to the minimum value in sediment transport. There is more sediment being moved around on the terrestrial landscape and in the ocean. And because of that, the worry is that there's going to be a great chance of counting the same sediment mass more than once. And so we choose the coastline because if you can get these values, these fluxes from the land to the sea along the coastline, you have a smaller chance of counting the sediment mass more than once. So that's why we use this accounting practice. And I am going to tell you about gigatons. Many of you have already heard me talk, and so you may not know that much about a gigaton. And basically a gigaton is 2.5 Great Walls of China. And it's 10 to the 9 metric tons. It's a lot of sediment. And we're talking about gigatons per year. So we're talking about the number of Great Walls of China per year that sort of encapsulates all this sediment that's being moved off the landscape. Okay, another concept before we get into the talk is this idea that we've gone through a planetary change, that during the Holocene and the times before that, our climate, our sediment flux, and most other things related to the surface of our planet were being constrained and driven by the Milankovitch cycles. This is the orbital changes of our planet. You know, its wobble, its axis, its precision, eccentricity. And those were the drivers of the Holocene and the times before. So when we talk about the Anthropocene, we're talking about that we've gone from those drivers to another set of drivers. And those drivers are human induced. So that includes population, the amount of energy that human population is consuming on an annual basis, and the productivity that, you know, how that energy is being distributed and how it manifests itself. And the reason behind this change in drivers, these change in human drivers, is because most of the environmental parameters, whatever you choose, that are global in scope, I should say, tie to one of these drivers. So if we were to look at how much reservoir capacity has happened over the history that we know of in the Holocene and Anthropocene, we could see that reservoirs capacity tracks intimately with energy consumption, or CO2 tracks intimately with energy consumption, atmospheric CO2. Or for instance, cement production or plastic production, they track intimately with global GDP. Or ammonia production or copper production, they track with human population. I think I've gone through this in a previous talk, but I want to remind people that it's because of this discovery that we talk about the human drivers of population, GDP, and energy, because so many of these environmental parameters track with them. Okay, now for the talk. So in the Phanerozoic eon, which is sort of the eon of life, 541 million years, studies have suggested the terrestrial flux off the landscape into the ocean, again, they are using the same accounting scheme that I talked about earlier, is about 5 gigatons per year. So whatever that is, that's 12 Great Walls of China per year on a global basis. And you can see that the Quaternary period is a little different. It's 2.58 million years, and it's more than double that longer term Phanerozoic eon flux of 5. So, and a lot of people have suggested that's because of the growth and retreat of continental size ice sheets. And because of that large impact on the landscape, fluxes have gone up, largely during deglacial. And so if we looked at the Holocene deglacial period, which is about a 5,000 year long period, fluxes are even larger than that. But if you then fold in and see where we've gone since that deglacial period, the last 6,700 years, it's gone back to the Quaternary average of around 11 gigatons per year. And again, I just want to emphasize that I think this is where a community has to get behind and review every single one of these numbers. Now, a couple of people have come up with what they considered an Anthropocene flux, and Hook, Wilkinson, and the number they came up with 75. It was a startling number when they published their values. And so part of our review was not only to review what they said, but to sort of do it ourselves all over again to make sure that it was, we could agree with their number. And the number we got for 1950, which could be considered the beginning of the Anthropocene, is 73. That's pretty close to their 75 in our review. And no matter whether you take their numbers or our numbers, it's vastly larger than any time in the Holocene, any time in the Quaternary, and any time throughout the Phanerozoic that we're aware of. So it's a big number, and it suggests that humans are really involved in moving and adding to this terrestrial flux. More importantly, and I'm going to walk you through this, is that the Anthropocene around 2010, the number has really gone up to the point where we're now an order of magnitude or more than these earlier periods. And that's kind of shocking too. It's not only shocking, but if you just go back a few years, 60, 70 years, to the beginning of the Anthropocene, we weren't expecting this number to be as large as it is today. So I'm going to walk you through this. So first, I'd like to acknowledge the fine work that colleagues from Asia and elsewhere have done in looking at some very large or medium-sized deltas in Asia and how they've come up with fluxes in millions of tons per year. Now, they were using terrestrial deposit dating. I think that's a really good method, and it's a reliable method. When you relate those terrestrial deposit dating methods to river fluxes, you then have to get involved in how much sediment is being stored on the delta and how much is getting into the ocean. So those are details. So let's focus on the green. If you focus on the green, you'll see that the Yangtze is the only one that covers the entire Holocene. And that's because some of these earlier times, North Grippian, Greenlandian, they're harder to come by because the Megalayan age deposits of the Holocene cover them up, and drilling is not always able to access them because you need very long drills, and no one's willing to pay for that, at least to the extent that you can totally get a good value for these numbers. So we have smaller time periods during the Holocene that the Songhong, the Huanghe, the Godavari have been measured across. And you can compare these values with these river loads values. And with them, if you look at the brown values, you can see that they were high at the beginning of the 1950s, and they're decreasing because of dam trapping. And so when we were doing the review, we actually thought that we should see the Anthropocene numbers go down from the 1950s, not going up. And we had these numbers staring at us. So again, that's something to keep in mind. So if you're looking at one of these budgets, it's really an accounting scheme. You've got the shoreline, so you're going to measure or try to determine the fluxes that are from coastal erosion, tidal erosion, the amount of sediment blown off the landscape, anything to do with the glaciers, such as subglacial meltwater, icebergs, maybe how much is being produced through weathering and hill slope erosion, how much of that material gets to the coastline through fluvial transport. And you'll be looking at suspended bedload, dissolved, and particular organic carbon fluxes. So the diagram you're looking at is for 2010, and the value we get, putting in the best numbers we could get a hold of, is 17.3 gigatons per year. It's hard to get time. No one does an international 1950 study of what happened in 1950. So you always have to get numbers sort of around those dates. And then you have to get numbers sort of around 2010. That's where the approximation comes in, because it's hard to get everyone in the world working at the same time to get one of these numbers. So even these numbers, as good as they are, involving thousands of papers, thousands of studies, still has a lot of error involved. So you have to admit that and try to refine that also over time. So let's start with the rivers, since that's the largest method of getting sediment off the landscape. And I put a few studies down here that either John Milliman or myself or those who worked with me have been involved with over a 40, 50-year period. So in '83, John did a study with Bob Mead, and if you took into account bed load, you get a value around 15 gigatons per year. They based it on good data on 70 rivers, and then they did continental yield scaling. And then Milliman and I wrote a paper in 1992, and that number went up to 20 gigatons per year. But then we had based it on 280 rivers and their fluxes, and then we use continental yield scaling. Now, we started to get into modeling because there are lots of rivers of the world, and you want to get that scaling right, and continental yield methods aren't that great. So we had 340 rivers to calibrate our models on. And we then modeled 4,124 rivers to get values between 14.1 and 15.5 gigatons per year, including bed load. And you can see that these numbers have fluctuated over time. And if you took some study that I was involved with, Irina Overeem, where we pretty much modeled the entire globe, 6,292 basins, including Greenland. So our numbers were getting, really getting refined. So it was a bit of a shock when we actually said, well, let's go back and update these many rivers with known observations that have been updated since these early published values. And when we did this, the numbers fell to 7.5 gigatons per year due to trapping largely, although there was some offset from meltwater. Well, I'll talk about that in a moment. So some of the reasons the numbers have fallen were based on some of the early numbers around 1950. It was a methodology. There were basically two camps who did the Amazon, and one camp really pushed for the 1 billion to 1.3 billion gigatons per year being the flux out of the Amazon. And other people said, no, it's more like, in the 300 to 600 million tons per year. And it was a methodology fight. And our study has now sided with the lower value. So in this case, it wasn't necessarily because a dam trapping was a revised number. So I wanted to emphasize that there's some methodologies involved in this. So, and when you look at the 10,000 plus rivers in the world, you have to admit two things. Of these 10,000, most of them don't deliver much water or sediment. And so it's not a numbers game per se. You can have 454 rivers deliver 90% of all of the sediment discharge, and maybe twice that deliver 90% of the freshwater discharge. So those are the rivers that you want to concentrate on, and perhaps with a scattering of ones that are smaller that may, for one reason or another, go from one side of that domain to the other. So even though there's 10,000, trying to get a 10,000 10,000 river number is not the best approach in this world. The other thing is that this paper was just submitted, Sagi Cohen and co-authors, and they started modeling bed load. And when you model bed load, you made us model a suspended bed material load, which then gets involved with wash load in the lower figure to be the suspended load. And so you now are starting to get a complete picture on the sediment flux coming off the landscape. Now, in our review, we did not take these new numbers into account. In our review, we had about 1 gigaton per year, and which is pretty much what the Cohen study got also for 1950. But we've said in 2010, this number is much less because of two things. One, there's less water flowing to the ocean. You have to take that into account. And the second thing is, you now have so much mining of sand and gravel along rivers. In fact, there's more sand leaving the river channels than is flowing along the river channels now. It's a completely different world. That number has dropped to around 0.3. And while this 19 gigatons, when you take from wash load and the 2 gigatons per year from the suspended bed material load, in other words, the suspended load, our value is more like 15 based on the literature and observations. In 1950 and 2010, it was 7.5. So there's some changes compared to a model. Okay. And let's get a look at how some of these manifest itself from observational data. In the Chinese River, 1954 to 2015, we can see that off of the landscape of China, it's gone from 2 gigatons per year, 1954 to 1968, all the way down to 0.3 gigatons per year, 2004 to 2015. It's an 84% decline. With this particular study that I was part of, it was very informative, and I urge people to look at it because it tried to examine where the sediment was getting sequestered. How much of it was getting sequestered in dams? How much was it because of the way the water was getting dispersed in canals and agricultural use and things like that? All of this can sometimes change how we view where the sediment is going when we see a huge reduction. This, I hope you've all seen before. This gives you a scale of the number of dams that are now on the landscape. And in terms of large dams, they're the ones that trap most of the sediment. They're trapping around 3,200 gigatons of sediment since 1950. And that's because the reservoir capacity has gone from around 685 cubic kilometers in 1950 to 15,000 since cubic kilometers of reservoir capacity. A lot of trapping going on. So we're left with trying to revise a diagram that Albert Kettner and I and others were involved with. So we are revising these now. In this column down in the Anthropocene 1950, that was based largely on upscaling these river observations. And now we see in 2010, these are the new numbers. And you'll see a couple of things. One is there's a lot less sediment flowing into the ocean. I guess it doesn't matter what the reason is, but there's a lot less sediment. We think most of the reason is still sediment dam trapping, but it's also methodology that we're now seeing better methods, better values. Second thing is some of these decreases are being offset by increases. And that's particular in Greenland, where you have meltwater offsetting these fluvial loads. Again, these fluvial loads are not taken into account aeolian or other methods, and it includes both suspended and bed load. Okay, let's move on to some of the other methods of getting the sediment off the landscape. So coastal erosion is this 0.5 gigatons per year due to coastal erosion is a weak number. We need to really get a better number on that. I think some people have tried and failed, I may suggest, to revise this number. Excuse me. So I think we need to do a better job. And this is where an international community should really work together on getting a good number. I think a single small group should not be the ones who come up with this number. It's too hard to do that. And there's too much work involved in any particular one regional area. So this is an example where we know from good mapping, good studies that the Indus Delta has lost about 47 million tons per year due to coastal erosion. Combination of tidal erosion and coast wave erosion, but mostly tidal. And is another study down below where the Chalfreya Delta is being retreating more than 1 kilometer since this study began in 1950 at the beginning of the Anthropocene. So those are some examples. So we really need to do a better job in this 0.5 gigatons per year. And all I can say is that it's a bigger number than that. We don't know how bigger. So when it comes to aeolian transport, there's too few in our community that are working on this. And we need, I don't know, we need 100 more scientists to work on this problem. So, but there are some studies that are putting out numbers, and you need to know the mean wind speed. You need to figure out what areas that are susceptible to wind erosion, and you start needing to apply some models to look at these fluxes. That's one method. Another method would be just looking at what's in the atmosphere and getting some satellite methods, environmental data records that you can integrate through the atmosphere on how much sediment would be in the air, in the troposphere, and arrive at these numbers. So when we say that there's about 1.5 gigatons per year blowing into the ocean, you can see from these diagrams, there's much, much, much more aeolian sediment blowing around the landscape than is getting into the ocean. And you can also imagine it's not like putting in a gauge in a river to get a flux. It's more difficult to get these values. So our community needs to work on that. Okay, so natural methods, even though they're impacted by humans, include icebergs. And this is a value that's been really going up from around 0.7 gigatons per year to around 4 gigatons per year, 3 or 4 gigatons per year. And it's, I don't know if everyone realizes that even off of Greenland, more of the fresh water is getting into the ocean by icebergs than from meltwater. So getting that flux from icebergs is an important value in the global sediment flux. Meltwater, subglacial meltwater, we know has gone up just from the volume of meltwater that's being released by glaciers from 0.2 to 1 gigatons per year. So those two values are going up. And most of the other values perhaps are not. Coastal may be going up though, I think. And so dissolved load, I think our community spends too much time on particulates. We need to spend more time on the dissolved load. They're part of the sediment flux. And when we say the dissolved flux has gone down from 3.5 to 3.6, that's again modeled on the lack of fresh water getting to the ocean. But there could be other reasons that change the flux of the dissolved load that need to be taken into account. And more studies globally need to be addressing this problem. So let's look at some of these other terrestrial production fluxes rates. So often we get really good values for 2010 and less good values for 2050. So we have to scale these 1950, excuse me, values. We have to scale them from the 2010, and we can scale them using some of the scaling parameters we see on the side, like human population or various metals or cement production or GDP. And we can test whether these scaling methods work, and they work really well. So I don't think you need to worry about so much about the 1950 values per se. There's more problems in other areas to work with on. So on the global erosion side, we had around 25 gigatons per year in soil erosion on the landscape. That's already larger than all the flux being moved off the landscape into the ocean. So it's already a high value. And it's a high value due to the human contribution to soil erosion. Now that number has increased to 75 gigatons per year, and a lot of it's due to cropland, and we write about this in great detail, compared to deforestation. So again, major areas for us to work on. Global construction has increased by 200%. Mining waste and production has increased 910% since 1950 to 2010. Global aggregate production, 1.6 to 50 gigatons per year. Sand and gravel mining, we've gone back and forth on this number. Again, we really think our community needs to get involved more. It's gone from 0.1 to 2 gigatons per year, and it could be higher. There's so much illegal mining in the world now. There are some places in Brazil that we know there's more illegal mining than legal mining. So, I mean, when we put these numbers out, I would say they're tentative. On the consumption side, you'll notice that the total is not the same as the production. We haven't tried to close this, but we know that there are some big areas that we are consuming the sediment. We don't really count consumption in our sediment budget. It's just how we use the sediment. So we can say that sediment that is being trapped in reservoirs is consumed 65 gigatons per year compared to 2.8. And only when we open up these dams, release the sediment, can we move that consumed sediment back into production. That's just our accounting scheme. Highway consumption has just skyrocketed and uses an enormous amount of sand and gravel. Coal consumption, it's gone up. Global concrete consumption skyrocketed up. And so we get this value that, again, is about half the value of our production. And just as an example, to remind you how much sand and gravel goes into a road construction, it's about 1.25 gigatons of sand and 1.9 gigatons of gravel per road kilometer. And so it just uses an enormous amount of sand and gravel, thus all the mining and illegal mining that goes on. So we have this diagram, and we have the two sides, and we have these numbers now that you can see for the total. And remember, we're not including the consumption, only the production in these total Anthropocene sediment loads. And maybe I didn't say much about all of these numbers, but when the paper, I can send you the paper when it's in press in a few days. We also take into account dredging, which has gone up on the coastal zone. We take into account some of these other things like trawling on our continental coasts, 2.9 all the way to 22 gigatons per year. So the humans involved in sediment transport and fluxes is enormous, much higher than any of the 7 authors thought when we set out to do this paper. So that's how we got these numbers that we showed you in the earlier part of the talk, the Anthropocene being 73 in 1950 and 300 in 2010. I'd like to take you now into a field that I think we really as a community have to get our act together and work much harder on. We should really accelerate this. I consider this low-hanging fruit. Some of this other stuff I talked about was very difficult. This is less difficult, but it's expensive. It's expensive. We know that the Earth's oceans have warmed. We know that the rivers are starting to warm. We know that atmospheric temperature is warmed. We need to take into account the manifestation of this warming on sediment transport. And one of the manifestations is sea level rise. A lot of people are working on that. But I think on many of these subjects, not enough work is being done. So let me walk you through some of these global warming, global change sides to the sediment flux, global sediment flux story. So we are having methods developed where we can look at, let's say, a large subcontinent like Greenland, and we can monitor all the rivers on a daily basis or on a every so often basis with satellite imagery and techniques. And we can combine it with field surveys and studies to make sure that those techniques are holding. And when we do this, we can get numbers that are in themselves stunning. I mean, did you know that Greenland is shedding 8% of the sediment river fluxes going into the ocean? I mean, that's a big number that we didn't know about. Or that most of the load is, as I said earlier, is by icebergs, because now there's just so many icebergs that are being calved into the ocean, both from Greenland, Antarctica, and some of the smaller glaciers in Alaska and other places. And we have to take into account how sea ice, which we've been losing 300 cubic kilometers per year, that's 275 gigatons per year of Arctic sea ice, has been lost since 1980. Huge changes on our coastal environment. You've got thermal erosion, you've got changes in the fetch that feeds the waves that then attacks these coastlines. Big problems, too few studies. I mean, when we did our review, we were surprised. We thought, so few studies, why? So our community has lots to do. When we come to changes in temperature on the landscape and how much sediment is being fed into river systems, we've known for some time that that warmer basins produce more sediment that is carried by rivers. So it feeds more sediment becomes available. And more recently, we know that when you warm the landscape, the biggest effects are in these cold basins, these subpolar and alpine basins. They have a really huge impact on sediment flux. So while the tropical regions will have a little bit of a bump in terms of sediment flux, it's really the polar and subpolar regions that will shed sediment. A recent study I was involved with that's now out in Science looked at the fluxes in rivers that are draining the Himalayas in terms of how much more water is being produced from melting of the glaciers and snowfields, and how much sediment from that flux is being carried by these rivers. And there's, I don't know if we should have been surprised, but there's a huge change in the volume of water and sediment that these rivers are carrying. And this is done all before dams intercept these rivers. So these increase in fluxes aren't necessarily getting down to the coastline, but they're filling up these reservoirs even faster because of this flux. And so, that while meltwater is increasing, on on a percentage basis per decade, 15, 20, 25%, there's an ever increase flux in the sediment load on a percent basis per decade. So the sediment is flashing hot in these areas. So maybe we walk down a rabbit hole. There are quite a number of people who are working on fires and the impact of fires on sediment flux. I'm happy to report. But there's so much more work to do. We're starting to get an idea from the kind of mapping you see in the upper left diagram that, we know where areas are getting burnt every year, sometimes for agricultural purposes. And we know the areas that are getting burnt because of human activity and our ability to fight these fires and in flammable invasive species and our poor historical management practices. But in the US alone, we know that 355 square kilometers per year is increasing in the size of these fires per year. And the number of fires are increasing. And we know that on the landscape, fluxes, sediment yields are skyrocketing to some of the highest yields in the world because of fires on the landscape. So it's really how we can take this information and come up with better flux numbers. You've seen this diagram constantly, but today I just want to focus on the sediment side to this simple equation. Our deltas are sinking because we're pulling a lot of water out. This accelerated compaction, human-induced subsidence, it can produce some of the biggest numbers. Like on the Yellow River Delta, we were getting values of subsidence of 250 millimeters per year. That's the largest value change that we can see that these simple equations can get at. So that's something to keep in mind. Are things like isostasy, used to see change in the E value, the used to see. Those values are increasing, sea level is rising, but they're not creating big numbers. Another big number area is how much sediment gets to the coast, because you can get really large sediment fluxes that can basically save a delta from sinking. Many problems with this flux number is that you can get the sediment to the delta, but if you've got all these levee systems and just move that sediment across the delta into the ocean, you don't change the sediment flux into the ocean, but you certainly change how much sediment is being sequestered by the delta. So studies that have gone on in the past, you may want to worry about whether those studies have a time dependency to them and whether that same time dependency on sediment trapping has changed. Some of you have seen this diagram. Every image is a year, satellite images on the Mississippi Delta. So now I want to talk to you about, so in this case, a lot of people were thinking, yes, it's sea level rise. Other people thinking it's sea level rise plus subsidence from gas mining, a lot of gas mining. Other people have said, well, yes, but the sediment flux to the delta has decreased by at least a factor of 2, maybe 3, maybe 4. And maybe the sinking of the delta is some combination of all of it. It's really important for this land to sea community to sort out what is the attribution of why a particular delta is sinking. It's nice to know that it's sinking, but we really need to know the why, because when we know the why, we can start to model that likely better around the world. So we need really good studies in more environments to arrive at some of these numbers. So I'm getting close to wrapping up. I've got 1 or 2 more slides. First thing is to say is that when you are talking about 750 Great Walls of China being produced per year due to human activity. So that's a number that everyone has to sit back and say, holy smokes, what are we doing to our landscape? When you translate what that means to building a Great Wall around the Earth's equator 151 times per year, we have to question how our humanity is behaving on the landscape. So when my co-authors and I developed this review, we were left with an idea that we need to have a grand challenge. We needed to develop a comprehensive, authoritative science-based geography of the cycle. We need to update contemporary baseline from which we would feel confident forecasting and hindcasting, going backwards. We need to evolve new databases and knowledge and simulations with data integration and intercomparison capabilities. For that, we can look to communities like CSDMS to help lead us in some of these data integration, modeling, simulation experiments. And we have to really involve the social sciences. The more I look at this study, I just don't know how we can continue writing scientific papers if we don't talk about the human side to all of these things. So I will leave it at that and take any questions. I have no idea whether I've talked more than I should have, but I'm stopping now.
Professor Syvitski, excellent talk. Many thanks. Okay, now if you would like to ask a question, you can unmute yourself and go ahead, ask a question. If you would like to type your question in the chat box, you may do so as well. So if you are using Zoom, there's actually there's a reaction button on the bottom, so you can also click raise hand. Any questions? Okay, I got one from Dr. Yijun Xu. You raised your hand. You can ask a question now.
Thank you very much, Jaia, for your great talk. I have a question about accounting based on data collected from the current river gauge stations. And as we know, basically all sediment data or majority of sediment data and also discharge data are connected from stations that are hundreds of kilometers away from the river mouth. And as the sea level rises up and the siltation backwater zone will move inland. So what do you think about the role of this measurement, the location on the sediment fluxes to the ocean, how much that could make to, in terms of error estimate, you know? So like we use sediment data, discharge data for the Mississippi River, and basically from the station at Harbor Landing, which is 500 kilometers away from the river mouth. And we also found increase in siltation in this 500 kilometer range from head of the passage to Harbor Landing. That's very similar, like in the Yangtze River in China, from Datong to the mouth, which is about 700 kilometers. So what do you think about this?
So, yeah, and you know that I've written about this muchly. I think that it's real. There are many aspects to your question, and I'm trying to sort them all out in how I can best respond. So one of the methods that our Asian colleagues did on these four deltas, the Godavari, Yangtze, Wanghe, the Songhong, was this terrestrial deposit mapping. So it's true that they couldn't go back as far as they wanted with their methods, but those values are pretty good. But the question our authors were asking each other were, well, what's the sediment trapping? How are you dealing with that sediment trapping, and what's the sediment trapping for the modern fluvial monitoring methods we're using? And so, I mean, Yoshi was saying that, well, you know, some of the sediment trapping for two of the Asian rivers was like 90%, 85%, 90%. So there's a lot of sediment trapping. But when we looked at it in more detail, we never were completely clear whether that trapping was on the terrestrial part of the delta or in the submarine part of the delta. We knew there was trapping, but how much was getting out onto the continental shelves was another thing. So there is that sort of big scale side to what you're talking about, is even linking these two different, very different methods. On the sort of in the engineering world, we've known that this is a big problem, and people who have worked on this have said, well, can models help us out? Can models help us out? Because when you add on that other 500 kilometers of unmonitored landscape, that's a big square area, a square footage area that you're adding to the whole thing. You're adding a great area. So is that great lowland area adding sediment or soaking up sediment along the way? And if we were dealing in a geological world where rivers behave like they should, this would be a much worse problem, because you would have a lot of sediment getting over the levee systems and onto the landscape. But where you're having river systems around the world, now not a particular river, but most river systems, they're so well leveed because they don't want the lowlands to flood, that there's really now a flushing system going on. So the things we would have worried about sequestration of the sediment in the lowland areas, or very little of that sediment getting moved out into the landscape, it's less of a problem. It's certainly a problem that we have to account for. And here's an example. So I worked on the Po Delta system, and I was looking at data from back to the 1930s to the present. And when they really put in high engineered levee systems so that no sediment was going to ever get from the channels to the delta, we were finding in the channels themselves that they were growing, accreting, whatever the word is, aggrading, between 3 and 10 centimeters per year. They were really collecting a lot of sediment, as you mentioned in your question. And to the point where we were having super elevated levee channel systems going across the delta. So the delta was sinking, the channels were growing, making the danger of flooding even greater. So the question becomes, in terms of fluxes, how it would change many things. Well, it could be a 10%. It mostly affects big river systems. So let's start with that. So maybe globally a 10% error. But the problem we have with that error is we know that it might be a 50% error in one river, a 0% error in another river. And so if you're working on a particular river, I'm not sure how much we can use that information to really upscale that new information to providing a better value. But it's certainly something that community has to work on. there should be a sub-community of this new grand challenge where people try to get down and address this. And for all the reasons you say, backwater effects, some of the other estuarine dynamics, we really have to do a better job. And I want to support your interest in getting a better handle on this.
Thank you.
Thank
Hi,
you, Professor Syvitski. We have a question in the chat box.
Can I ask one question?
Who's this?
Hi, it's midnight. I'm speaking from Bangladesh.
Oh,
Thank
sure,
you
go
very
ahead.
much. Thank you very much for this nice presentation. And you have mentioned about the impact of dam and the sediment budgeting. But in our context, in the Ganges Delta, you know, and you have publication on Ganges Delta, we have a huge number of boulders, coastal embankments, and they are, you know, playing a very important role in sediment budgeting and rebudgeting and distribution. And if it is the scenario, how do you think the global context, this coastal boulderings and embankments playing an important role for sediment budgeting?
Well, to begin with, you don't have a natural system. Let's be honest. There's no natural system on the Ganga Brahmaputra Meghna Delta. It's not a natural system. The Brahmaputra River is a little bit more natural in how it functions than the Ganga Delta. The poldering is a big problem because you put the polders up to protect it from, in many cases, to protect it from these cyclone-induced storm surges. There are many problems with that. One problem is that some of the storm surges are over 6 meters in height. They can overwhelm these boulder heights of 4 or 5 meters. And then you put a lot of coarse sediment pushed over during these storm surges. They add sand to the farmland, and that's adding of sand basically has ruined the farm fields for a long time. It's way more work to get that sand out, to get the get that farming soil back to where it should be to grow crops. So, I mean, there's some human side to this story that you're more than well aware of. But in terms of the global flux, yeah, so the poldering is a problem that affects sediment getting onto the landscape, and once you get it on the landscape, ever releasing it from that poldered area. So it's like a permanent trapping per se, unless you take out the polders. So I think that it's more of a local thing, even though it happens in not just Bangladesh, but many countries. It's a local phenomena that restricts sort of the positioning of sediment rather than the global fluxes per se. That would be my response.
Thank you. So we have one question from the chat box, and this is from Fang Yao. So Professor Syvitski, you estimated a 65 gigaton per year of sedimentation being trapped. Could you briefly introduce the data sets and approach to get this number?
Yeah, so well, that's not my number. We didn't get it. We just, we went to the International Commission on Large Dams, and we used values that they had commissioned and got. United Nations very worried about this, and their interest may shed some light on the answer that you're seeking. They put a lot of, World Bank and other organizations have put a lot of money in building dams around the world to increase agricultural capacity or hydroelectric capacity and the reasons you build dams. And this money is predicated on how long these dams will not fill up, how long they will last. And so if they fill up much faster than people think, you're basically you've thrown money at a problem that is not solving. In fact, is causing more harm because, well, when you build a dam, you're solving problems, but you're also creating problems downstream. So they put a lot of effort into going on these large reservoirs, doing repeated measurements. Echo sounding is probably one of the best methods to do it, and looking at how fast that aggradation is growing. And most dams that are sort of structurally run by engineers, they will be working on how fast sediment is getting sequestered. There are more classic ways of getting at this number that the community has worked on, such as what's the flux going into a dam, which is the flux leaving the dam, and you just subtract the two and you assume that that difference is the rate the dams are filling in. You then have to take into account, and no one does this, but you should take into account, well, how much sediment are you pulling out? Because reservoirs are also being mined for their sediment. And they're mined usually when the reservoir goes down, they go in with loaders and trucks and backhoes, and they fill up truckloads of sand and gravel at the head deltas of these reservoirs. So that has to be taken into account too. Those are the methods that are behind the ICOL dam system. They're pretty good. There's been 2 or 3 large commissions that they've funded that try to get at this number. And since ours is a review, we haven't done the analysis ourselves, although we've been involved in some of the numbers behind an individual dam or two. It's those numbers that we're using. Thank you.
Thank you. We have multiple questions. So Mohammed Risha, number 1, Pauliu, number 2, Mike Steckler, number 3. Okay, so Risha, could you unmute yourself and ask a question?
Hi, Professor. This is Mohammed Risha from NC State. First, thank you for the presentation. It was like a big sandwich of information. That's great. My question is specifically about the Julian sediment contribution. You mentioned about it. I want to know, is that much big, the contribution of the Julian sediments to the ocean, and what methods could be used for quantifying these amounts of sediments?
Say that again.
The methods, or the methods used to quantify the Julian sediments contribution to the ocean.
The alien sediments. Okay. There's, as far as I know, there's 2 methods that I'm aware of, and I'm not involved in this. So again, this is something we're reporting on rather than being the scientists behind the numbers. The 2 methods are, you have a map. It could be a soil map or a landscape map or some set of maps of where sediment is subjected to wind erosion. And you then run wind models across those landscapes, so they would develop some sort of entrainment function. They would develop, what level of winds you need before you would get any movement of sediment, and just the normal stuff that sediment transport people do. And they would run the numbers to find out how much sediment would leave the domain and enter the ocean. So that's method number 1. Whether you like it or not, that's method number 1. Method number 2 is based more on observation, because aeolian transport, dust transport, is something that can be detected by satellite systems. And so we're now no longer talking about what's on the land or what's being detected in water, but what's being detected in the air. So with those typical reflectance methods that are looking at different wavelengths that would detect airborne particles, you can use them, in fact, to calibrate the models that we talked about in the first method. And in almost all cases, they use satellite methods. So in a way, you can say satellite methods are the dominant methods. But you can also use satellite methods that would get an integrated atmospheric flux. They call it the dust flux. And NASA produces these flux numbers on a regular basis, on a daily basis. But I think they're applying basically what's called an environmental data record and an algorithm that will convert that environmental data record to a set of what they call sediment or dust flux numbers, integrated flux numbers. They then will take the pixels of the coastlines, and they would look at, since you don't get aeolian sediment generated in the ocean, it's only going in one direction. They would then assume that those fluxes are the ones that are getting into the ocean that cross that coastal pixel. So they often report this, and you know, I'm talking in a field that I'm not an expert on, but they've developed these methods largely because of volcanic eruptions, where they need to know, the airline industry needs to know how much volcanic ash and at what elevations and what concentrations and what particle size and what the thermal properties of this flux is to get at the contribution in the atmosphere. Sometimes scientists use this to find out how much sediment is being blown from Africa to North America, or Asia to North America, or Europe, or whatever. So there's some reasons behind these developments, but I'm not an expert, and that's pretty much all that I know on the subject.
Thank you. Paul, you are the next.
Yes, hi, Jai. Thank you very much for this fantastic talk. I have a brief comment and also a quick question. First of all, in terms of the dam trapping rate, I searched 100 of rivers, but I only found one solid data. One large river is the Nile River. Some colleague from Egypt, they document very well the high Swan Dam trapped more than 95% of sediment. They even mapping inside the reservoir to show the delta, the volume of the delta with timeline progression. So if you need, if you don't have, maybe you already had the data, if you don't, I sent to you. They show nicely yearly by yearly how much trapped behind the dam. And I try to get a similar number from Yangtze or other river system, but haven't successful yet. But this is something we can work together for the future. This is a comment. A quick question. I'm so amazed about your number come out. Compare the 1950, 70 gigatons, but now 300 gigatons. You know, we haven't get a chance to read your new paper. My question is, what does 300 gigaton meaning for us? Is this the number delivered to the river, or is this the number of the river basin can produce? Definitely, we know this is not a number reached to the ocean. Yeah, how do we interpret this 300 gigaton? What that mean, the number?
Yeah, so that's very good. Yeah, you can imagine the authors on the paper were trying to also get our hands on all this. So only natural fluxes, air, wind, rivers, glaciers, coastal erosion, those are the only ones that we can talk about in terms of flux from land to the ocean.
Okay.
So those numbers, in the paper, we keep them separate so that everyone can see how these can be separate from the amount of sediment that is being eroded from croplands. And the reason, so that becomes part of the Anthropocene flux. And you have to understand both of these two numbers, because if you're producing a lot of sediment in one and you're not increasing the flux in another, then you have to say, well, where is the sediment going? In the soil erosion, what we've determined from the papers and many studies is that soil erosion doesn't transport very far.
That's right.
And so it's eroded off of this part of the landscape, but maybe 20 kilometers away, it's not even showing up. We did a study, I was involved in a study in an area where we were interested in deforestation on a high slope, the Andes in Colombia. And what we determined was, with a 33% increase in soil erosion from this deforestation, you only got a 9% increase in the river flux. So those two numbers then become important, because then you can say to yourself, well, where did that difference go? Well, they're filling in lowland areas, gullies, different places. They're getting trapped on the landscape, but they're not on the agricultural soil area anymore. They've been moved off of that into some other area, lakes and other small streams. Second thing, and I think this community really needs to understand this probably better than other communities, is that there's an inherent lag time in everything we talk about. So you can cut down a landscape, you could have a lot of soil erosion from cropland development and farming and agricultural practice, but it could take hundreds of years for that to march its way down from small streams to large streams into the big system. And so when we detect, that's why we think we should include this soil erosion, when we detect the sediment flux increasing in one of these big domains, it will eventually show up. How long it takes, we don't know. And that's where we need to, I don't know, there are radiometric methods to try to get at lag times in the systems. And the lag time in one river system may be different than the lag time of another system. And so it may come down to individual studies in different places.
Mm-hmm. Okay, one last thing. You know, a decade ago, when we have a river class, we were taught the sediment yield is just about the sediment flux divided the basin size. But actually, you know, nowadays we see the dam can reduce sediment flux, but the dam or reservoir cannot reduce sediment yield. Do you agree with this?
Well, I mean, it's like any accounting scheme, you have to know what the accounting methods are.
Yeah.
I mean, I don't think it's a big problem as long as you all agree on the methods.
Yeah,
if you are putting a lot of, I mean, yields, it's a funny number. It has different meanings to different people. So for those people who just take river fluxes and divide by area, that's a different meaning of yield than somebody who's talking about the yield from a particular part of a landscape due to fire and deforestation has shot up by 1,000 times to have a higher yield. That yield is not landscape, the drainage basin yield. It's a landscape element yield. And that's what I'm trying to say. Those landscape element yields don't necessarily translate to river basin, drainage basin yields in easily accountable ways. And how we scale between them can be very different. So whatever method you use, you just got to agree on. So if we had the community sitting around a table, if you were to set this up with 10 other people and we had a few hundred people in the audience, you would have to go through what you mean by different accounting. And even if you didn't use that method in your previous studies, as long as everyone agreed to go forward, this is the method, we would have a good accounting system. But what we can't have is everyone coming up with their own accounting system.
Thank you. Thank you.
Okay, thank you. We have two questions from the chat box. The first one is from Mike Steckler. Second one is from Amelia Paskowski. So Mike, would you like to unmute yourself and ask a question?
Sure. And first, since you were just talking about the fluxes, the 1950 earthquake in Assam released about 10 times the annual Brahmaputra flux. And what you saw is the fine grains reached the coast relatively quickly, and the coarser grains, moved down the coast over decades, multiple decades it took to reach the coast, altering the rivers as it went. But what I was going to ask was also on the Ganges Brahmaputra. The estimates are of the sediment flux coming out of the river mouth, about 10% goes along the coast and gets swept back on shore. So it's a significant flux there, and probably in some other major rivers like the Amazon, where there's a lot of long strike transport. But you said you neglected that kind of from sea to land flux. So I was wondering.
Yeah, we generally do. Gene Turner and others on the Mississippi has talked about how the storm surges from hurricanes have pushed sediment back onto the landscape. No, when we wrote the paper, we were very aware of all of these studies that suggest, but on a global basis, there wasn't enough evidence for us to include it in a budgeting system, because we're now talking about not just 3 or 4 or 5 locations, but we're talking about the entire coastline of the world, number one. And not all coastlines are impacted by storm surges.
Right.
But we also don't, and you're not really talking about storm surges, you're talking about tidal pumping,
right,
keeping sediment inside, quiet water environments. So that would enter what we did on the coastal flux side.
Mm-hmm.
So the coastal flux should not be considered a one-way, you erode a shoreline and that's the only way it could go. And so for those studies, like the one I did on the Indus, we were looking at how the entire shoreline changed from 1950 to the present. And so if that would incorporate any storm surges or coastal erosion and give you a net flux. And so when you do those kind of studies, you in essence take that all into account. Where you're going to base it just on a series of numbers, how much that comes out of a river, how much is moved back on land, or how much the coastline is being eroded. When you're basing it just on that and nothing about how the area of the land is changing, then you have difficulties in trying to really close those budgets. Another thing I would add, since you brought up this trapping in the tidal channels of the Sundarbans, is that the polders, because this was asked before, they do impact these numbers greatly. And so if you don't have a really good method of taking account how much sediment is getting sequestered, it's almost like you can throw out a number there, but you might not. That number is a very unconstrained number. And for many of the studies that have actually, like, again, my colleague, Eugene Turner from LSU, or not LSU.
Yes, from LSU.
Yeah, LSU, yeah. Yes, you would know. Their numbers are poorly constrained.
Yeah.
You know, they wrote these papers in Science, but you know, if you were to say, well, how accurate is their number? They took too few samples.
No.
If you were to look at even the numbers that were coming out of the Ganga Brahmaputra Delta, you know, those are weak numbers. They're not strong numbers. Those are weak numbers, and I think our community could do a better job. You know, we had colleagues putting in sediment traps on those tidal channel areas and trying to find out how much sediment was getting deposited there. I mean, when you do those kind of studies, you can start getting really good numbers, but I'm not so sure that we certainly can't do it for the world. And I think we can't do it for probably 95% of the world. So the numbers are weak, and that coastal erosion thing, yeah, it's probably the weakest number in the whole budget.
Yeah. And
at least the Aeolian numbers, you can get a global flux, whether the algorithm's good or not, you can still get a global flux, but with these numbers, really difficult to get a global flux. And the previous person that asked about the trapping, you know, at some level, you can only trap so much before it either shows up in the landscape as a shoreline progradation, or it shows up as a shoreline erosion. It has to show up, because if it doesn't show up in a very near future, it's not trapping, it's not changing much. And I think that's where we are with the GBM deltas, that when you look at the satellite imagery, things haven't changed in many of those places in a couple hundred years. And especially on the Indian side of the delta, maps back then and maps today haven't changed much in the last couple hundred years about where the shoreline was. If it was trapping a lot of sediment significantly, you would see progradation.
yeah, and the Indian side is more losing land, and the polders are mostly keeping sediment out.
Correct. So it's
Okay.
a difficult number.
Oh, thank you. We have one question from the chat box. Amelia, are you there? Do you want to
Yes.
unmute yourself? Go ahead. And Philip
Yeah,
Hill is the
thanks.
next.
Thanks a lot, Jaia, for this really interesting talk. I guess my question is about scale. I was wondering how such like global sediment flux values could be used at the regional scale, especially in deltaic nations, for sediment management decisions.
Yeah, so that's truly source to sink question. Love your last name. Just had to throw that out there.
Thanks, like yours too.
So, yeah, so sediment management. There's, I mean, your question's so complicated. Oh my God. The first things one would be trying to figure out is, what does sediment management mean to your particular delta? For some deltas, maybe the Danube, for an example, though the sediment management there is try to keep certain ecosystems healthy. And sediment management would be looking at well, what is a healthy environment for how much sediment arrives or is getting eroded from a particular area, and what its impacts are on bird migration or seagrasses or whatever. So there's that kind of sediment management. In many areas where people live, sediment management has nothing to do with that because those natural systems are long gone. And sediment management has everything to do with agriculture. And it has to do with agriculture in 2020, maybe perhaps differently than 1950. In 1950, these deltas, sediment management was about rice farming, the rice bowls of the world. In 2020, you might be, they're the protein bowls of the world. So it's shrimp farms, agriculture in general, aquaculture, I should say in general. And those interests are very different, extremely different. There you're talking about cutting down mangrove forest, that and putting up polders and other levee systems to try to keep out or mitigate some of the sea level fluctuations that the mangroves would have put in place. So global numbers, they have great meanings to many people to know the scale of the problems we have. But I think in general, you're still down at the catchment scale. You're trying to look at what does your catchment have and what does your engineering world look like? What are your systems looking like? Less so than it might be how much of your carbon, nitrogen, phosphorus fluxes are tied to sediment, and what does that impact the ecosystem? So like I said, it's a very complicated set of topics you're trying to deal with, and not all global flux numbers will translate to meaningful management decisions at the local scale. However, if you got some idea of what perhaps you're missing, maybe you're in an environment like the Indus where there's an aeolian flux that's quite large. Most people, when I looked at the literature, they never took that flux into an account. So maybe global numbers and where numbers are getting generated could impact you to say, I should look at that. I should look at this. The dissolved load is decreasing. I need to take that into account. That's maybe how you could look at it.
Thank you very much.
Could I ask a very quick follow-up question to that?
Sure.
Very, very quick, I promise. So in this new study that is going to be published now, because I saw in your talk that the greatest contribution is from rivers, do you in the paper kind of attribute that sediment flux to some of the world's mega rivers in terms of regions? Like, do you split that into Amazon, GBM, and so on, or do you talk about it as one global flux?
Well, different papers have talked about it differently. In this particular paper, we were trying to get at what could be considered the great geological cycle, the sediment cycle, the one where tectonics is balanced by erosion and flux off the landscape into the deep sequestration of the ocean. So those are the big, the big geological scale things. That's where these numbers were coming from. And that's where we're so surprised that the Anthropocene side has changed so much. And I've lost my train of thought, but I'm really an old person. So, you should expect perhaps that I lose my train of thought once in a while. So what was the question going for?
No, I was just checking whether you're talking about regions, but I appreciate that's
the region
talked about in different papers. Yes.
So our paper didn't talk about that. Other papers have. I think that if I got anything out of regional, I was totally unaware of that. For instance, the mining of the Mekong River it's pulling out all the reaches, not just in Vietnam, but in Cambodia and upstream. The mining is, I think it's around 100 million tons per year of sand, gravel, and other sediment is pulled out of that river. And yet the sand transport down the river is 6 million tons per year. So you've got, no matter how you scale that, if you continue mining at that pace, you will have used up all the available sediment. And so you'll get a system that has no bed load simply because there's no bed load to get at. And so I think illegal mining and legal mining of river beds around the world is something you have to get your hands on. And I don't know how you do that. Satellites probably can help, as you can see the lineup of trucks going to get this sand. And there are certain places in South America, India, and China that are just hopeless when it comes to illegal mining that is unreported. And that makes me think that we don't really know when there's so much that is not even published. So I'll leave it at that.
Okay, thank you very much.
Thank you so much.
Thank you. The last question from Philip Hill.
Hi, Jaia. Hope you're doing well.
Hope you're doing well.
Great talk, thanks.
Are you still
Jennifer says
director?
to say hi as well.
Are you still director?
Oh, I'm retired emeritus now, like you.
Oh, yay!
My question actually follows Amelie's point, a question about delta management and
Okay.
what you were saying about your grand challenge. And I'm wondering, you mentioned, for example, needing to bring in sociology and other aspects of, management of our world, I guess. And I wonder if what you mean by that is perhaps a greater role for civil society in general. So I'm thinking about the Fraser Delta, for example, which you know well, and recent events. We've just had major flooding events in the Delta, and the question of how you manage a medium-sized delta in this case, but with multiple jurisdictions and different kind of levels of government getting involved and trying to coordinate how you manage a relatively big system like that, both politically and socially. And I'm wondering whether, in order to address the grand challenge, we really need to kind of pull together kind of networks of stakeholders around the world to kind of mobilize a little bit in terms of supporting the kind of initiative you're talking about, but also in terms, for example, of standardizing methodologies, the way we manage the information, the data that we need to manage delta systems. And if a proposal of some kind is going to be developed, whether it should be broader than just the academic questions of sediment fluxes, but actually try and bring in those groups that need to be involved in management.
Absolutely. You picked a topic where there's at least some level of interest in coordination. Living with Delta is an organization trying to figure that all out. The Dutch are trying to do this. They're battling amongst themselves because you have those in the Dutch community that are wanting to build coastal barriers. They're really good at it, and they know about it, and they know about the downsides, the bad sides of coastal barriers, and the good sides and how to do it. They're on that side of the, and then you're the others that are saying, you know, that that's admitting failure. And the Dutch community, they're saying, no, we should be flooding the landscape naturally, experimentally, so that we build up and degrade the landscape. So even within a country where there's some sort of coherency in scientific thought, they disagree on how this can best be done. I think these disagreements are real. I think these disagreements need to be sorted out. I don't know how much scientists can contribute to that. I think what scientists can provide them is the latest methodologies to accomplish information that they can make a decision on. Ultimately, it will never be the scientist's decision. I think it's important that, for instance, if someone was to, let's say, take a series of cores and you could tell a manager, this is how this delta worked for the last 10,000 years. This is sort of how often we see natural floods contribute to sediment on this surface, and frame it nature. That's almost like the hockey stick of the CO2 in the atmosphere. You're giving them a baseline from which you can then build on human effects on that history. They may appreciate that. But I think that when it comes to Delta health, okay, so the little I've got involved in this is that, you know, people have asked me to comment on what's going on in the Mississippi Delta, where there's been some suggestions and some active experiments of trying to build deltas in different places. So I don't know what a scientist can contribute to that. Whatever place you pick may not be the perfect place. It may be the perfect place that an engineer suggests because it may protect a city or a community or an industry, but it may be hopeless other than for some short-term protection. But to the engineer and to the Delta manager, they may think, no, I know it only will last 10 or 20 years, but that's better than not lasting any time at all. To the scientists, they don't know what the meaning of that is because that's not their bailiwick. Their meaning is, in 100 years' time, this Delta will not be here. You know, that's sort of a scientific number we can sort of arrive at. I think that if we were, you might not be able to do that. I'm trying to give you an answer that I don't know if I can give you. I don't know if it would be good to have engineers and social scientists and historians in the initial development of a sediment grand challenge community where you're planning scientific developments when those people really could care less about anything other than their domain. But they might be, we brought some of those same types of people when we were working on dams and dam sequestration. We all learned a ton that we never learned. So on one hand, having some experts who have this sort of practical experience in the room with you, that certainly can help. But whether they should dominate the community as the community goes forward in the scientific world, that I think I would leave to the people who aren't retired. It could change the very nature of how you do science in a good way, or it can contaminate it and get it off message and get it so focused on humans' concerns about stakeholders and things like that, that we've lost the ability to get some of these large scale numbers. So I don't know if I have an answer.
Great, thanks. I didn't really expect an absolute precise answer to that question. I'm just, I guess, just generally asking the question as this kind of research moves forward. I think, as you say, the next generation will have to take these kind of networks of interested parties into account when they're designing studies and trying to find the best research.
Yeah.
Okay, I think that's it for today's webinar. It's already 2:45 a.m. Beijing time. So I really appreciate everyone's participation. We still have friends and colleagues from Asia. This is amazing. We had 72 participants.
Yoshi is still here. I'm not sure he's falling asleep or not. Yoshi is 3 a.m. maybe. So thank you so much. This is fantastic. Everything is recorded, and this is the legacy. This is great. And so, Jaia, to be honest, it looks great. When you give it almost 2 hours talk, you still full of energy. That's amazing. So I'm looking forward to your new paper.
I'm with Phil. I retired.
Your mind never retired.
My mind never retires. I love you all. Let's get together sometime when this pandemic is over.
Sure, definitely. Okay, we should have this talk somewhere near the Great Wall. Then you can point to the Great Wall to talk about.
Yeah,
Okay.
Thank you so much, Professor.
Thank you, everybody. Have a good winter break. Okay.
Thank you.